Now we're into the energy aspects, which of course when studying kinetics dominated by the activation energy. Here we have a very standard reaction. Sketch on axis the energy profile for the reaction, labeling activation energies, forward reverse reactions, and the change of the reaction. Well, when you have a one-step reaction, these pictures only vary in whether or not the products are higher than the reactants when delta H is positive, or lower than the reactants, as is the case here, when delta H is negative. Reactants, products, transition state or activated complex, take your pick, and the energy difference there is the activation energy. Okay, so a very standard thing, the difference between the products and the reactants, minus 114 kilojoules here, that's your delta H, and minus tells you that the products are lower than the reactants. The energy change is such that the reaction has lost 114 kilojoules. Now this one, interestingly, likes to bring in both the forward, going from there to there, and the reverse reactions, going from there to there. So for the forward reaction, the activation energy is from the reactants up to the peak here. Okay, and for the reverse reaction, which is where these suddenly become the reactants, is going all the way over the hump from that direction, which is this one right there. Okay, so very, very standard diagram. Not often you see them asking for the reverse reaction, but the activation energy for the forward one, EA, and of course delta H. And the reason why they wanted this was so they could ask this question here: what's the enthalpy change of the reaction delta H in terms of the activation energies? Well, here we just apply Hess's law. We can go from the reactants to the products, go down this direction, so that's minus 114, or we can go in this direction, as I will draw right there. Okay, so if we go directly, minus 114, if we go indirectly, we have to go up the EF and down the EB, or in other words, EF minus EB. Just a very straightforward application of Hess's law. So we're going to see this type of question many times. Graph shows the distribution of energies in a sample of gas at a certain temperature. Sketch on the graph the curve obtained at a higher temperature T2. Okay, and so what you see there, this is, excuse the fact that it sticks out over there, very hard to control the mouse when drawing these things. The average energy is increased. This is the average energy, or actually the modal energy at T1. This is the modal energy at T2, and the temperature spreads out the range of the possible energies. Okay. Explosive has an enthalpy of detonation minus 1106. Sketch the energy profile again. Well, again, we're going to use this one, in which the products are lower energy than the reactants because delta H is negative there. Okay, so minus 1106, and the activation energy, just worried about the forward reaction going from the reactants over the hump right there. Activation energy for the explosive detonation of RDX, 199. Activation energy for mercury fulminate, 105. So activation energy, energy needed to kick-start the reaction, right? You can have all the collisions you want over here with the reactants, but unless a collision has the energy to get over this hump, i.e. in this particular case, 199 kilojoules per mole, that reaction is not going to happen. Now, when we compare the two of these, for RDX, the collision has to have 199 kilojoules to get over the bump. The mercury fulminate only has to have 105. So its bump is lower energy, thus it's easier to get over the hump. Thus mercury fulminate, with the lower activation energy, which is easier to get over, is going to be less stable than the RDX. Same old picture, distribution of energy particles in the gas. On a graph, draw the distribution of energies of the same particles at higher temperature. So lower temperature, there's the reaction shaded in blue, right? And this is the wrong question, right? It's not the energy that the particles have, it's the energy of collisions. Okay, you've always got to have a collision in order for a reaction to happen, according to the collision theory. So it doesn't matter what energy the particle has, it's the energy of the collisions that we need to plot here. But we'll pretend that this is the right question. So therefore, the particles' collisions, right, that have the higher energy at the lower temperature, shaded in blue. Now let's increase the temperature. Okay, doing that same stupid picture that we had before. And so what we're seeing here is that we spread out the energies. The typical collision has a higher energy at the higher temperature, and so therefore we will shade that particular amount in red. So more collisions, right? Even though, of course, if we actually drew this properly for collisions, this wouldn't look like this. It would be higher energy, and it would be higher because there are more collisions at higher temperature. But anyway, there's the shading that they're looking for. So a prettier version of the same picture, the reaction profile here. So obviously the reaction itself is exothermic to the tune 98 kilojoules per mole. And what we have here is the decomposition of hydrogen peroxide. Normally it has an activation energy of 75 kilojoules per mole. So they tell us in this first part, when we use manganese dioxide as a catalyst, it lowers the activation energy. Draw the reaction profile for the catalyzed reaction on the board. And what they're looking for is for you to just draw a lower hump, right? So there is the hump when it's 58 kilojoules per mole, going from 100 up to about 158 as the activation energy. The better profile would be one that emphasizes not only is there a lower activation energy, but it comes because of a different mechanism. So I would actually draw it with that same energy hump there, sort of trying to get it there, but at least an extra little hump. So here's 2 steps for the reaction with the activation energy of 58 kilojoules per mole. To be honest, I don't know what the A-level boards want there. I mean, the important point is showing the 58, but I would also like to emphasize, well, there's a different mechanism too, goes from 1 step to 2 step in our pretend hydrogen peroxide world. Now on to the Arrhenius equation, always great fun. State the Arrhenius equation. Well, K, the rate constant, which we know for this question, by the way, is equal to A, which we're told, okay, times e to the power of minus EA, which we aren't told, at temperature, in this case 300 K. So there's the Arrhenius equation. And calculate the activation energy using this catalyst, hence state was a more effective catalyst than MnO2. MnO2, remember, had a activation energy in the last question of 59 kilojoules per mole. So we plop in all the values that they give us, using R is 8.314 joules per mole per Kelvin. And we get this, 1.68 for the K, 1.41 times 10 to the 4, e to the blah, 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 blah. Now, take your time in doing these questions. First thing I would do is I wouldn't touch the E thing. I'll just divide both sides by 1.41 times 10 to the 4, or bring the 1.41 times 10 to the 4 over to this side, however you want to put it. And that gives us 0.000119, right? 1.68 divided by 1.41 times 10 to the 4, 0.000119. Now let's punch this into our calculators, okay? After taking the natural log of both sides, taking the natural log of this side gets rid of the E, taking the natural log of this side gives us minus 9.035. And now we can just rearrange quite happily for EA. Notice both sides are negative, so the negatives cancel out. And EA is going to be 9.035 times 8.314 times 300, which is 22,535 joules, or 22.5 kilojoules. Now, 22.5 kilojoules for this new catalyst, 59 kilojoules per mole for manganese dioxide. Obviously, the activation energy is lower for the new catalyst, so it's going to be better. I'm sorry, I said 59, I obviously meant 58. Rated constant to temperatures given below. Not overly sure why they gave you both of these, unless they want you to plot a graph and then read things off that graph. Much easier just to solve it using one set of these data. So anyway, the activation energy, I'm going to use the logarithmic version. So I'm taking the natural log. So natural log of K equals natural log of A minus E over RT. By taking the natural logs, we get rid of that little E. Okay, now we're told various sets of conditions. At 300k, so t is 300, k is equal to 0.2873. So we'll pop all that in. We knew k, we knew the activation energy. Notice I'm using joules now. 79,333 instead of 79.333 because R is 8.314 joules per mole per Kelvin. So anyway, looking at all this, I can figure out that natural log of A is equal to 30.56. Okay, just going through this, natural log 0.2873 is 1.25. Everything punched together in here is 31.81, so natural log of A is 30.56. Now let's think about what's happening at 295, which is what we're interested in, where we don't know k. Punch things in, log of k, same log of A, same activation energy, same R, different t. Put in our value of log A that we got up here, 30.56. Get natural log of k minus 1.79, and so k is 0.167. Quick sanity check, if you like, on this. 0.167 for 295. Well, 295 falls between 288 and 300, so k, our 0.167, will fall between these two values, as it does. By the way, the answer key also gave a point for calculating the value of A, 1.87 times 10 to the 13. Absolutely no indication in the question that one had to do that. So why would you give a point for calculating that? I don't know. But anyway, k 0.167. Don't worry about units because it's not showing them. 20. So go back to our iodomethane and thiosulfate at a range of different temperatures. If you remember, you got the rate law for this earlier, but that is irrelevant. What we want here is it tells us it got rate constant at a certain temperature, tells us the activation energy, notice kilojoules, which we'll undoubtedly have to turn to joules. There is the frequency factor, second order reaction units, as you see up there, because it told us it was somewhere second order, or it told us the units of K up there for the second order. Find the temperature used. So we pop everything in to Arrhenius, 3.1 for K, 5.62 times 10 to the 12, then E, there's the activation energy, there's R, there's T, again solving it out. Do the easy calculation first, now get rid of the E by taking natural logs of both sides, and we get this, and now just bring the T up here, the 28.226 down there, and we get T is 346 Kelvin. Multi-step reaction, NO2 plus CO goes to NO plus CO2. Rate equation is K times NO2 squared. This first step is the step that leads to that rate equation. Rate determining step is the step of the mechanism that's slowest, and that goes straight in to the rate law. Now, writes equations to show a possible two-step mechanism for the reaction. Now, what's important here is that there's two steps, and that the first step involves two molecules of NO2. After that, we can sort of play with that second step as long as we end up with this overall equation. Now, of course, one of the things we have to do in that second step is make another NO2, because the whole reaction requires one NO2 as reactant, and we're using two of those. So we got to later on, i.e. in the second step, make another molecule of NO2 to counter that. Okay. Now, our product on this first step, okay, two things we can do. We can just have the reaction between them giving us an intermediate of N2O4, right, 2NO2 goes to N2O4, or we can make one of the products, which would have to be NO, and then make another intermediate with what's left over. Well, if you've got two N's and four O's and you take out an N and an O, you're left over with an N and an O3. So two possible first steps. Okay, and then as I say, the second step has to produce an NO2, right? And it's also got to react, something's got to react with CO, which is the other reactant that we haven't used yet, to produce whatever the products might be. So in our first step for this possible mechanism, the intermediate N2O4, that's our first step, 2NO2, got to have that, making N2O4. And then that N2O4's got to react with CO, because we need a CO in there. got to make CO2 and NO because those are the products, and then we've also got to make an NO2 to get back to only having an overall of one NO2. In other words, when we add up these two steps, the N2O4 intermediate cancels out, the NO2 we made in step 2 cancels out with one of the NO2s we used in step 1, giving us the overall equation. The other possibility, two NO2s make an NO3 plus that NO that we said. So this is where the option where our first step makes one of the reactants, and then that NO3 that we don't want has to react with CO to make CO2, the other product, plus that other NO2 that we talked about, getting back over here. And so add all those together, the NO3s cancel out, the NO made here with one of the NOs with which we started again, and we get the overall reaction. Okay, the really crucial parts there, first of all, that your first step involve two NO2s, because that's what the rate law says you have to have, that you end up after taking the first and the second steps together with the overall equation. How you get there? Well, two immediate ways pop to mind. I'm sure you can think of other weird, strange ways to do things. Back to the iron and the tin reaction, if you remember that from earlier, rate law was K times N2 plus times H2 plus. Students suggest the rate determining step is Fe3 plus Sn2 plus, so using two of the reactants goes to Fe2 plus, one of the products, and an intermediate. So off the top of one's head, nothing immediately wrong with that other than everything. First of all, of course, the rate determining step has to match up with the rate law. Okay, the rate law includes H plus, so the rate determining step must have H plus somewhere in there. It doesn't. Okay, as chaps, rate determining step includes Fe3 plus, so Fe3 plus would have to be in the rate law. It's not. And then finally, from a chemical point of view, tin 2,3 highly unlikely to be involved as an intermediate. I mean, you can get tin 2,3, but it's a very fleeting existence. So it's tin 3 plus, very fleeting existence. So probably not going to be anywhere near the mechanism. Catalysts, very important industrial processes. How do catalysts increase the rate of reaction? Well, they speed it up by providing a different mechanism that has a lower activation energy. How do they affect equilibrium? They don't change the position at all. You just get to equilibrium faster. And here we're back to our energy distribution curve. So E1 is the activation energy without a catalyst, and there is the fraction that react. And then we put a catalyst in with EA2, so taking the same picture, that was our EA1. Okay, EA2 going to have a lower activation energy, thus is going to have more reacting. Again, they're saying molecules, it's actually collisions that are important there. Okay, so lowers the activation energy, therefore more possible reacting species. And we've done all this over the way for question 25. Not overly sure why I included it, other than for comprehensiveness in pulling out all of the questions. And 6, iodine intermediate conversion of methanol to ethanoic acid. One catalyst is the iridium-containing complex ions. That's iridium with 2 carbonyl ligands and 2 iodides. It's an example of a homogeneous catalyst. A homogeneous catalyst is one that's in the same phase as the reactants. So therefore methanol is a liquid, so this will be either a liquid itself or much more likely just dissolved up in your solution mixture, which indeed is the case. Why is transition metal complexes can act as homogeneous catalysts? Well, first of all, of course, you have to be able to dissolve them up in the particular solvents, and that depends on one complex to another one. But what they're looking for here is that transition metal complexes have 2 really important characteristics. The first is they can add and lose ligands quite happily. So you've got coordination sites available to allow your, in this case, methanol to bind to the metal ion. And the way the A-level likes to say this is there's bonding orbitals available. it's actually the coordination sites that are available that's more important. And then there's multiple oxidation states available. So most catalysts actually function, or an awful lot of catalysts function via redox reactions. They add on a solvent with an oxidation, and then they kick it off, the new product, kick it off with a reduction. But that's something we will actually talk about in a later extension module. That was question 26. I think that was it.